At first glance, piezoelectricity seems like a beautifully straightforward phenomenon. Apply mechanical stress to certain crystalline materials, like quartz PZT, lead zirconate titanate, or gallium nitride, and they generate an electric field. Compress, twist, or stretch them, and charge appears on their surfaces. This effect powers everything from ultrasound devices and inkjet printers to energy harvesters and nanosensors. And thanks to well-established equations, we can predict how much electric field should result from a given stress. But under certain conditions, particularly at the nanoscale or in highly engineered materials, something strange happens. The electric response can exceed what those equations predict. This puzzling deviation is known as the piezoelectric overcompensation. Let's take a step back. In classical theory, the piezoelectric effect is linear. The electric displacement charge density is proportional to the applied stress governed by the piezoelectric coefficient. Everything fits nicely until it doesn't. Experiments have shown that in some cases, piezoelectric materials generate stronger electric fields than expected, not just slightly stronger, but significantly, as if the material is overcompensating for the stress it's under. What's going on here? To understand this paradox, we need to zoom in, literally. Much of the overcompensation behavior appears in nanoscale structures, thin films, nanowires, and layered composites. At these scales, materials no longer behave like their bulk counterparts. Surface effects dominate, atomic arrangements become more strained, and interactions between domains or interfaces can cause nonlinear responses. Imagine a piezoelectric film sandwiched between two different materials, each with its own lattice constant. If there's a mismatch in how the atoms line up, the film experiences built-in strain even before any external stress is applied. This strain can align the dipoles inside the crystal more tightly, effectively preloading the material. Now, when you apply external stress, the internal response is amplified not because the rules are broken, but because the initial conditions are far from neutral. You might ask, but aren't these effects already accounted for in advanced modeling? Not always. Classical piezoelectric theory assumes homogeneous, isotropic conditions, perfect crystals, and ideal interfaces, but real materials are messy. In engineered nanostructures, there can be internal electric fields, charge accumulation, grain boundary effects, and electrostatic feedback loops that aren't captured in basic models. These can all contribute to field amplification, a kind of cascading response where the polarization feeds back into the stress, enhancing the overall effect. Another factor is flexoelectricity, a lesser-known cousin of piezoelectricity. While piezoelectricity arises from uniform stress, flexoelectricity results from strain gradients, how quickly strain changes across the material. At small scales, these gradients can be massive, especially near edges or interfaces. The result? Additional polarization on top of the expected piezoelectric response. And in thin films or nanobeams, this flexoelectric contribution can rival or even surpass the conventional one. There's also a quantum twist. In some materials, particularly ferroelectrics, quantum mechanical effects and electronic band structure changes under stress can cause enhanced charge separation, pushing the electric field beyond classical limits. In engineered superlattices, where different materials are layered with atomic precision, interfacial coupling can create synergistic effects, leading to giant piezoelectric responses that seem to break the rules. So how can a material produce more electric field than predicted? It turns out the answer is not that the theory is wrong, but that reality is richer and more complex than the original models assumed. Piezoelectric overcompensation is a sign that we're entering regimes where classical approximations fall short and where nanoengineering unlocks behaviors that bulk materials could never exhibit. Could this paradox be useful? Absolutely. Overcompensating piezoelectrics could lead to ultra-sensitive sensors, high-efficiency actuators, and energy harvesters that squeeze more electricity out of less motion. In nanomedicine, these materials could be used to power implants or deliver drugs with precise mechanical control. In microrobotics, they could provide lightweight, high actuators far beyond current capabilities. But it also means researchers must rethink design principles, simulation tools, and device expectations. Predicting material behavior at this level requires multi-physics models that include mechanics, electrostatics, surface chemistry, and quantum corrections, all interacting in nonlinear, often surprising ways. And perhaps that's the true beauty of the piezoelectric overcompensation paradox. It reminds us that even in fields we think we've mastered, there are still surprises, that at the edge of classical understanding, materials begin to write their own rules, rules shaped by atomic detail, interfacial complexity, and the hidden interplay of forces we're just beginning to map. In that flicker of excess voltage lies a deeper truth. When we push materials to their limits, they sometimes push back with more than we expect. Piezoelectricity is the property of certain materials to generate an electric charge in response to applied mechanical stress. When these materials are deformed, the displacement of ions within their crystal lattice creates a voltage across the material. Classical piezoelectric models predict a linear relationship between the applied stress and the resulting electric field. However, under certain conditions, some materials produce electric fields that significantly exceed these predictions, creating the so-called overcompensation paradox. Researchers have demonstrated that single-walled carbon nanotubes can carry electrical currents far exceeding those of copper wires, which could lead to ultra-efficient nanoelectronics. It's like discovering that a hair-thin fiber, when arranged perfectly, can outperform a thick, conventional cable in transmitting power and information. The overcompensation paradox refers to the phenomenon where certain piezoelectric materials produce electric fields greater than those calculated from conventional linear models under the same mechanical stress. This discrepancy challenges the standard understanding of the piezoelectric effect, suggesting that additional factors or nonlinearities may be at work. The paradox implies that the internal structure or dynamics of these materials can amplify the electrical output beyond simple predictions. Resolving this paradox requires a deeper investigation into the material's microscopic properties and domain interactions. Researchers have found that in some lead, zirconate, titanate, PZT ceramics, the measured voltage under stress can be significantly higher than what the linear piezoelectric coefficient would predict. It's like expecting a modest echo in a canyon, but instead hearing a sound that is unexpectedly amplified, as if the canyon itself is boosting the noise. Nonlinear effects occur when the relationship between stress and electric field in piezoelectric materials is not simply proportional, especially at high stress levels or in specific crystallographic orientations. These nonlinearities can lead to an enhanced response where small increases in stress produce disproportionately large electric fields. Factors such as domain wall motion, phase transitions, and microstructural heterogeneities can contribute to these effects. Understanding these nonlinear behaviors is key to explaining the overcompensation paradox. In some ferroelectric, piezoelectric materials, domain reorientation under stress can result in a sudden, large increase in polarization that exceeds linear predictions. It's like a crowd at a sports event that suddenly erupts into a cheer from a slight trigger, creating a wave of energy far beyond what one might expect from a single voice. The internal microstructure, including grain boundaries and domain configurations, plays a crucial role in the piezoelectric response. In certain materials, the reorientation or movement of ferroelectric domains under stress can lead to an amplified electric response. This domain dynamics introduces complexity beyond the idealized uniform crystal model, allowing for localized enhancements in polarization. These microscopic changes can effectively boost the macroscopic electric field, contributing to the observed overcompensation. Advanced imaging techniques have revealed that regions within piezoelectric ceramics exhibit significant domain switching under applied stress, correlating with enhanced local voltage generation. It's like a well-organized crowd that, when prompted by a small gesture, collectively shifts in a coordinated, powerful wave that far exceeds the impact of individual movements. Variations in material composition, dopants, and processing conditions can substantially influence the piezoelectric properties. These factors can enhance the mobility of domain walls or stabilize specific crystal phases that favor higher polarization. Optimized processing techniques can yield materials with superior electrical responses by tailoring microstructure and defect concentration. Such engineered enhancements may lead to the overcompensation effect, where the electrical output is greater than traditional models would predict. Researchers have demonstrated that doping PZT ceramics with certain elements can modify their domain dynamics, resulting in an increased piezoelectric response under mechanical stress. It's like adding a secret ingredient to a recipe that unexpectedly enhances the flavor, far beyond what the original ingredients could achieve on their own. Advanced theoretical models incorporate factors such as nonlinear polarization, dynamic domain interactions, and mesoscale effects to explain the overcompensation paradox. These models move beyond the simple linear constitutive equations and consider the complex interplay between mechanical stress and electrical response at different scales. They often utilize computational simulations to capture the intricate behavior observed in experiments. The improved models help reconcile the enhanced electrical outputs with the fundamental physics governing piezoelectricity. Finite element analysis and phase field simulations have been used to model the nonlinear behavior of piezoelectric materials, successfully predicting the amplified responses seen in overcompensation scenarios. It's like using a detailed weather model that accounts for local microclimates rather than a simple average forecast to predict a sudden storm surge in a particular area. The overcompensation phenomenon in piezoelectric materials has significant implications for energy harvesting and sensor technology. Small mechanical stresses can be converted into disproportionately large electrical outputs, which can be harnessed to develop more efficient sensors and power generators that operate under minimal mechanical input. Improved energy conversion efficiency can lead to the creation of self-promoted devices in various fields, such as wearable technology and structural health monitoring. Understanding and leveraging the overcompensation effect could revolutionize the design of next-generation piezoelectric systems. Enhanced piezoelectric materials showing overcompensation are being investigated for use in energy harvesting floor tiles, which can generate electricity from human footsteps far more efficiently than conventional materials. It's like installing a mechanism in a dance floor that not only captures the energy of every step but magnifies it, powering lights and devices with surprising efficiency. Accurate measurement of the overcompensation effect requires advanced experimental techniques capable of probing the microscopic behavior of piezoelectric materials under stress. Methods such as piezo response force microscopy, in-situ X-ray diffraction, and high-resolution spectroscopy are crucial for understanding domain dynamics and polarization changes. However, isolating the specific contributions of various factors, nonlinear effects, microstructure, and processing variations poses significant challenges. Continuous advancements in experimental instrumentation and data analysis are essential to fully characterize and harness the phenomenon. In-situ X-ray diffraction has been used to observe real-time domain switching in piezoelectric ceramics, providing insights into the mechanisms behind the enhanced electric fields. It's like using a high-speed camera to capture the split-second movements of a hummingbird's wings, revealing intricate details that are invisible to the naked eye. Future research will focus on further elucidating the mechanisms behind the piezoelectric overcompensation paradox and exploiting it to develop advanced materials with tailored responses. Innovations in material synthesis, doping strategies, and computational modeling are expected to unlock even higher efficiencies in energy harvesting and sensor application. The integration of these enhanced piezoelectric materials into practical devices could transform industries ranging from consumer electronics to aerospace engineering. Understanding this paradox not only advances fundamental science but also drives technological breakthroughs that leverage unexpected material properties. Ongoing research is exploring new composite materials that combine traditional piezoelectrics with nanomaterials to achieve even greater amplification of electrical output under mechanical stress. It's like discovering that combining two seemingly ordinary ingredients can result in a culinary masterpiece that exceeds all previous expectations, opening the door to innovative recipes and applications